Okay, so I have volume and I have enable. I'm on the process of extending the assignment, so we'll start lectures in just a second. This is all recorded. So let's go to Brightspace. Okay. And okay, so I'm recording these. So the issue is we need to, wrong course here, need to adjust the due date for assignment 2, because so officially you will be on your winter break. Are you on winter break on Sunday? Anyways, probably not a good thing to have it that day. So what we'll do is so you're still responsible. You've had it for a few weeks, but we'll have assignments 2 and 3. Like assignment 3 is going to be given to you guys when you guys come back, right? That Monday. So this is being recorded here. Okay, so let me go back to course home. No, course home. I'm going to go to share screen, start. Okay. So we are into tools. Oh, here. So we are into tools, assignment, and we'll look at assignment 2, and we'll edit the assignment. And right now is due on the 16th. So you have a week off, 17th to the 21st. So I was thinking about making it due on February 26th, which is a Wednesday, 11:30 p.m. Is that good? Okay. And save and close. Done. Okay. What is the going to be doing? So assignment 3 will be given on Monday when you come back. And assignment 4 maybe merge with assignment 5 if we don't have time. Maybe, well, not double, but just select the topics from it as well, right? So we'll have to look at that when the time comes. What? I really don't like GoodNotes, but you know what? My son is an Apple user, and he gave it to me, and he just forces me to have a confined. Use it. It's painful. Yeah, it's not as good as OneNote, but I want to stop sharing. So return to meeting and stop sharing. Okay, because I need to log in. So GoodNotes. Okay, favorites. So first thing is some admin stuff. Okay, so let's go. Let's go start talking about some logistics. The first one is assignment 2. I just is being recorded. I just extended the deadline for Wednesday, February 26th. Well, that's late. Okay, you don't want it that late, but it's fine. So Wednesday, February 26th at 11:30 p.m. So that's assignment 2. Assignment 1 will be given to you on Monday, February 24th, and we'll have 2 weeks, and then there will be. We have 3 assignments to go, 3, 4, and 5. But potentially, if we go right out of time, we will combine assignments 4 and 5 into one. So take half of each, the most representative designs. But I do need to cover all of that, and getting rid of one assignment is not going to help. So consolidating may be another option as well. Okay. Any questions on that? Number 2 is I'm actually physically traveling. If I can get a model, apparently it's 40 centimeters on Thursday. So there will be no lecture on, no live lecture on Thursday. But there's enough material, because if you went to the resource here on Teams, you'll see that I updated the class notes, and we now have a lot more content to work with. So I would like you. So this course is set in 7 modules, and we are already sort of in the middle of, or starting 4, which is the technologies and the signaling as well. Then we have one on timing and CDR. We have one on timing, another one on CDRs and clock data recovery, and the last one is on clock safety. Those are the 3 modules that are still missing. Module 5 is pretty small. Module 6 and 7 are pretty extensive, so I'll take us for the rest of the term. Go ahead, yeah. Okay, so no lectures on Thursday, but they will be, I can go through the rest of the slides and do a discussion, and I'll record it and have it ready for the rest of the week. Okay. Still, the material that you will see there is still not being asked on in assignment 2, so you should be okay. But we still need to cover it. We talk about bandwidth trade-offs. I don't want to spend too much time. There's a lot of slides in here. I want you guys to stop me when I say something that looks obscure and you really don't understand what I'm talking about. So let me ask you, based on what we've done so far, do we understand the issue with gain and bandwidth? How does FT and everything else comes into play? How we're constrained to speed in high-speed electronics, but there are some ways out. And those ways out is by using FT doublers. And what I mean by FT doubler is we basically break the dependence between gain and bandwidth. That's what it's all come about, right? And one of the ways that you do it, which was done by this clever circuit here, is that you get twice the current, or the current flowing, here's on the top side. So the current flowing in RF and R2 sets the transconductance of M1 and M3. So you have GM1 times GM3, because you're taking the output of the first and feeding it to the next one as well. So you're multiplying effect. So GM1 and GM3. But so you have potentially these two all have the same current and they're identical. You can have twice the transconductance. Right? And remember, FT is GM over 2 pi CGS, which I have right there in the formula. So if I have twice the transconductance, I have twice the FT. So twice the gain bandwidth product. So I extended the bandwidth of that circuit. But the problem for it is that making the device larger to get higher transconductance also require you to make it to increase its periphery, which increases capacitance. But do I have to do that here? I have 2 devices accounting for the transconductance, but the capacitance, input capacitance, which is what really limits that, is still just the capacitance of M1, right? So you get twice the transconductance. Let's go back here. Twice the oops, why so? Sharpness, pen style. Did this do it? Nope. Where is, okay, fountain pen sharpness? Is this the one? Nope. Oh, right here. Okay. Here. Okay. So we have I1 and we have I3, right? So those two will account for larger transconductance, but we only see the CGS of 1. So higher transconductance and capacitance still remains the same. Hence, we have increased, if not double, the FT. Okay, and there's different ways of doing these. I've shown you some feedback mechanisms that use series and shunt feedback as well. Okay, the second topic one of the last topics that we ended last time was the concept of gain peaking. So I sort of gave you a hint on how to do basic network analysis to come up with an equation that defines the input impedance to that circuit. And if we use normalization factors, such as the ones that I am suggesting here, you should be able to come up with a factor, a bandwidth improvement factor, which is related to M, where M is related to the L, or the peaking effect, right? So you have an RC circuit that we already had before. We're now introducing an inductance, and we would like to know what effect does the inductance does into the bandwidth extension of that specific circuit. So if properly done, you would actually come up with, let me see, normalized frequency, not showing here. But if properly done, what you will see is that there's an M factor or a bandwidth extension factor that would actually peak that inductor. And that inductor will actually change the transfer function of the circuit to give you a response on which you basically extend the bandwidth, right? So here's an example on this plot here, and I show you the case for no inductive peaking, or F1, versus the case for a lot of inductive peaking, F3, the actual curve in the purple, and then the one in between, which is the black, is L optimized, which actually is the one that gives us the best response and can be estimated by the equivalent function that I defined here at the bottom of this plot here. Question for class, when we talked about this, is if I get more bandwidth out of the purple curve, why do I need to back down and go back to the flat curve? Isn't the bandwidth the end game? Why bother? Why backtrack that, right? Capacitor effects, no, what I'm saying is I have control over the size of inductance that I can use to peak that circuit. But the larger I put the inductor, the more I peak it to a certain level. It's going to saturate eventually. But a large inductance, i.e. the purple curve, gives me larger bandwidth. But I often don't go that far, and there's an optimum value shown here in black, in the black curve, that actually defines the maximum inductance that I should use. So, but the bandwidth is lower. So what other performance indicator are we missing when we're making a decision? Yeah.
With the gain peak, isn't there also the phase change for the higher frequency?
Well, yeah. So first of all, there will be amplitude variations, which is not necessarily a good thing. Secondly, we haven't been shown here, but there's also phase differences that are actually going to change the group delay variation across from that. So, so we don't necessarily just want to blindly increase gain. We don't necessarily just blindly increase bandwidth. We want to increase bandwidth, but we also want to make sure that the group delay is within acceptable levels, so that when you're passing a large amount of data, all the data sees almost equivalent group delay, and that it doesn't get distorted on the other side, right? That's the end game here for that. Okay, so that's covered. And then different topologies. We talked about T-coil peaking. This is a very famous, commonly used extension bandwidth techniques in which you actually use two inductors, L1 and L2, but you also end up using a load capacitance, as you see here, to actually extend the bandwidth. So based on coupling between the two inductors and these capacitors, you can actually almost resemble a transmission line. The problem with the circuits, right, and where you lose bandwidth, which all comes back to, I'll show you in a second here. So you have some kind of an amplifier, okay, going into a chipset. So here's your IC. And that IC effectively onto a board. So you're on a PCB board. And that PCB board has a pad. So you have a bond wire and you have another bond wire. So you have bond wire 1, bond wire 2, and then you have this capacitance here that is needed for ESD, for all sorts of different things. And you got to have that. So if you look at the actual equivalent model of this, it resembles a series inductor with a shunt capacitance with a series inductor. which again has more stability and better frequency response than if we had an inductor alone. So we try to make it look like a transmission line by purposely slicing values of L and C. So if I control the values of L and I control the value of C, I would actually now have an impedance that could resemble or could be engineered to lessen the blow on this discontinuity. More importantly, if I actually introduce coupling coefficient, magnetic coupling between the two coils, I can further expand the bandwidth. And that's what the T coil does. And we'll leave it at that. Okay. Here's an example of what a circuit looked like. So this is a three-stage amplifier section. You have a differential input-output, right? And then you have effectively resistive loads all across. But if you look at it, and what's going to happen is this section here is going to have a low-pass filter response. And the next section, which I'm going to do in blue, is going to have another low-pass filter response, because basically all we have is R's and C's, right? But the one in the middle, which I'm going to do in red, is actually going to be peak, right? So that if I do the transfer function of the first one plus the transfer function of the second one, and I try to plot that in green, I would actually end up with an extended low-pass filter flat response. So the secret is that if you properly design this, when this device is actually peaking, that can be matched to when the device is actually starting to fall or roll off on the other side. So the peaking on one end compensates for the roll off on the other side. And when you have a cascaded effect, you can actually make it super flat. And that's what you do. You don't purposely just peak every stage. You have a roll off, a compensation, and a second roll off. Okay? So you have three design variables there to actually make sure that the final response, which is the green one, is extended and flat. And that is an analog equalizer. And we're going to learn about these in when we do equalization. And this is commonly known as a continuous time. This is not sample, continuous time linear equalizer, or CTLE, some form of it, which is based on inductive peaking and other parameters that we'll see as well. Okay. So inductors, and these inductors here can actually purposely be introduced, and you see them there. So in a final exam, I could say, what is the circuit used for? Describe the advantages and disadvantages. How is that going to make high-speed electronics better? And there is about a page and a half or 2 pages of discussions and conclusions that you can come up out of a very simple schematic of that. And that's the type of questions that I ask. I'm not going to give you values of 10 milliamps and use an equation to tell me what the delta T will be. No, that's what the assignments are for. But what is it fundamentally from a circuit topology that this circuit brings into the picture? And how is this circuit different? Now let's say this circuit. I notice how I'm focusing on a couple of circuits. I like the circuits, so maybe I'll ask something about that, right? And it is not to do to 3509. I'm not asking about that. All I'm asking is currents, conductors, capacitance, FE, F max. By equation. Okay. This one here, all I'm asking is do 501 principle of superposition here. We have amplification, we have transfer functions, they all add up. What do we need to do to make this work? And what we get out of such a circuit like that? And if properly designed, you know what should be the outcome, right? So let's see what they say here. Shunt peaking with spiral inductors is very efficient for bandwidth extension and switching speed up. However, spiral inductors are area expensive. And if you look into an RFIC, let me see if I can open this up here. Okay, so let's go into an RFIC layout. Okay, and let's look at images. I'm trying to grossly exaggerate one of these. Okay, RFIC layout, and I'm gonna say inductors. And the reason why I'm saying this is that when you look at, okay, let's look at this one. Okay, yeah, this one is a good one. So look at this. So if you look at the area of this is an IC circuit, right? You got paths, And those paths need to be because we need to have IOs. And then inside of it, you have active devices, but you got all these little coils. And those little coils are inductors. And those inductors end up taking a lot of space. So first of all, I said it costs $2 million $10 million per design cycle on a 7-nanometer FinFET technology. But why would I be paying $10 million to actually have metallic coils? I should really only be paying for the super small transistors that I need, correct? Because that's the one I can't have. All those big chunky coils that you see there, they can be implemented anywhere. So what happened here? Recording has started. Okay. Okay, well, you're saying 21 minutes, so, but we're not sharing anymore. We stopped sharing, so. Join. Am I not connected to Carlton? Yes, CU Wireless. What's going on? Okay. Share screen. If I stop sharing, I will encourage anyone to please let me know right away so that we, okay, so go here. So inductors use a lot of space, right? They're area expensive. And here's other examples that show you that. This one here has inductor peaking, see the inductor there. The last one as well has inductor of multiple stages, right? So you can do it on one stage or multiple stages for as long as you know what you're doing. Okay. We talked about the phase of the transfer function affecting the affecting different parts of the spectrum in different ways, and that has to be measured as a function of group delay. And here's the official definition for group delay, which is basically the change, the rate of change of phase as a function of the angular frequency, right? And typically, what we do is if we have a circuit, such as with a transfer function shown in black here, which is the gain, we can also plot the group delay, which is actually shown in blue here, and you will see that on around the edges when the gain begins to roll out, the group delay just shoots out, right? So you're going to have a figure of merit that will define how much group delay you can handle, and that would also ultimately affect your bandwidth of operation. It's not just the gain, it's also the bandwidth, right? And then, as you can imagine as well, because we're now looking into filtering techniques and bandwidth techniques, we also have to get into bandwidth considerations. So when looking at the transfer function of a low-pass filter, not every low-pass filter is created the same. You can have a Butterworth as well, or you can have a Chebyshev, or you can have an elliptical. And, you know, this one is maximally flat amplitude. You can have maximally flat phase, but there is another type of filters called the Bessel-Thompson. And we're not going to get into what they really are, but this is basically maximally flat group delay. And really all it has to do is that if I actually look at the locations of the poles and zeros in the circuit, it really only has to do with the actual angle, right? So if this is P1, the angle of which, if you were to actually plot the imaginary and the real part here, the angle in which the poles are located defines the actual type of filter that you have, right? So again, we're not really going to get into this. I'm not going to test you on this, but just to understand that those pole locations are actually controlled by RCs in your circuit. So Alexander, the PA, his job is PhD thesis topic is to actually use something in the circuit to control that angle, so that he can come up with the best possible amplifier based on a famous, hard to find Bessel-Thompson response. Okay, we'll leave it at that. Active inductor. So we said that inductors actually have an issue with the fact that they use a lot of space in silicon. So then what happens if I actually use a small signal analysis? We're not going to get into analysis, but just to define that we can actually look into the source of an amplifier and make it actually look like an inductor based on this equivalent circuit here, where omega t is effectively 2 pi of ft. So you have the transconductance and the capacitance of that section here as well as the R that we loaded with to actually calculate the value of inductance. So this here is called an active inductor. And the active inductor is actually defined in terms of the biasing, so the current flowing through it. So if you have current flowing through that transistor, it's going to define its transconductance, and it's also going to define the small signal capacitance, right? And that's also going to be modeled by using this additional experimental component RG to come up with a value of inductance that is actually usable and still very small in terms of layout, right? So I can actually use an active inductor, oops, to actually peak that circuit. So here, your active inductor. Now you have active inductance, right? So you have your DC gain on the red curve, which is effectively rolling off, and then you have in the blue curve a peaking component, which is this active inductor that actually compensates for that. So inductors can be used for bandwidth extension, but they are bulky. They use a lot of area, but they are very linear. Active inductors don't use a lot of area, but they are small signal components. They are not very linear. So question for class is, for everyone, what do I mean when I say passive inductors are linear and active inductors are not linear? What is your appreciation of that statement? What do I mean by linear? If I was to plot inductance as a function of the power that it sees into it, what do I want it to be? Do I want it to be like this, or like this? 1, 2, or 3? Which response would I like to see if I am plotting a, one of the characteristics like inductance, for example, L, as a function of power? I would like to see 2. I would like the inductor to be the same inductance regardless of what power I'm putting through, right? So when you have a piece of metal that is conducting current, and those fields are basically can be quantified in terms of the value of inductance that it can produce, the metal doesn't really care what value of the power I put in until it's about critical power to melt the actual metal, right? So that's very linear. If I do either a small power, medium power, or high power, I still get the same inductance. In here, if I put more power, then I start to violate the small signal behavior of the circuit. What does small signal mean? Back to 2507. What do I say when, let's say, for example, S parameters are small signal parameters? What does that mean? Yeah, so if you have a active device, and that active device, so I'm gonna put another resistor here. So if you have R1, R2, C1, and so on, right? So if you look at this active device here, showing this bipolar device, you have carefully sized the R1 and R2 to bias the transistor into its quiescent condition. Guys, understand what I'm saying by quiescent? We all know that, okay? So we have purposely designed these transistors so that it operates a given IC and a given CE and all the other characteristics to ensure that it's in saturation and all the good stuff. And that current also is used to define this DC conductance and the capacitance and FP and all the other stuff, right? But that's a bias point. If I actually put a signal into it or try to inject an AC signal into it, small signal tells me that the signal is small enough that it doesn't quite perturb the quiescent point of that transistor, so it still behaves the same. Right? Small enough that it doesn't disturb the biasing of that transistor, hence it doesn't change its transconductance, it doesn't change anything else. But the moment that amplitude becomes larger and larger and larger, guess what? Now the perturbance is actually considerably large enough that it can start to disturb the DC biasing of that, and that's no longer set to be a small signal behavior. You now have a large signal behavior. So active inductors, depending on what I'm putting into the actual source of that transistor, if it's small, it's not going to affect the current.
it's not going to affect the transconductance, it's not going to affect the capacitance. But if the change in current is too large, then it will. And as a result of that, there will be linearity constraints on which the active inductor would actually have to be designed, right? We can do the same thing with capacitors. We can store energy in a capacitor and release it just about when it's good enough to do so as well. So we can actually do similar efforts and actually add capacitors to actually do the peaking effect as well, right? So capacitor peaking introduces a zero or a zero peak, which generates the gain on low frequencies and removes the generation at high frequencies, right? That's effectively what it does. So you can actually translate this down into the gate. And it will basically what it will do is that it will degenerate the gain at low frequencies. So if you have a response that does this, right, it's going to degenerate at low frequency, but it's going to increase at a high frequency, right? And this is with C peaking. Okay, and that basically stabilizes the gain bandwidth behavior. So it's not rolling off, and it can be used to compensate that as well. So they're less deficient for bandwidth. They use less area than inductors, but they can actually help. And often we end up using them as complementary efforts. So capacitive peaking, inductive peaking, and active inductive peaking, all of those can be used together to actually form the best possible solution as well. This one here is actually very neat. So we learn about Miller effect, or who in this room does not know what a Miller effect is? Okay, so you have a capacitor across two terminals that have gain, right here. And that capacitor, by using Miller theorem, can actually be split into two capacitors, one to the left and one to the right. And the capacitance on the left gets exploded by the gain between the two nodes. And the capacitor on the right is divided by the gain between the two nodes. That's effectively Miller's effect in a nutshell as well. All right. And what we can do to cancel that out is we can actually use, well, we can do several things. First one is we can actually just put a cascode. Because if you do the small signal analysis of a cascode as we did in 2507 and 3509, you will see that effectively this transistor removes the effect of CPD. Almost like shorting it. It gets rid of it. Okay. Or you can actually have a capacitance that basically takes the opposite of the current and feeds it back at the input, kind of a feedback mechanism. Okay. So the current to the neutralizing capacitor is equal in amplitude, but it's opposite in size, which basically will get rid of the Miller effect. So the cascode is one concept, or we can actually inject a current with the opposite polarity to cancel out the Miller effect, as we do there. And we can do that directly with a capacitor, right? You can do it on the other side. So you have a CGD on both sides. And if you actually, so you have a CGD on the right and a CGD on the left. And if you introduce the opposite, so imagine the differential pair is basically moving up and down, right? So when one side moves up, the other one moves down. And effectively, the signals on opposite sides of the output of the differential pair are set to be at 100 degrees out of phase. That's perfect. So if I was to take the current from one branch and feed it to the other, the current branch from the other side and feed it to the other, I purposely done exactly what I set out to be there. It just cancel the Miller, the Miller capacitance, CGD. And that's what the circuit does. Every high-speed circuit that you will see out there in an integrated format at the moment actually uses neutralization capacitance. So if you go and look at the work done by AlphaWave or Sienna or any other company that is doing high-speed electronics, you can see that they will rely heavily on Miller cancellation by using these cross-coupled capacitors. You got the CGD, which is parasitic to the device, and it uses two neutralization capacitors, CN, but they have opposite phase injected into either one of those nodes. And that gets rid of that Miller capacitance and hence increases the FT of the transistor. Okay, principle of operation for FT. So you can either have input connected in series, in parallel, or you can actually have all the outputs connected together. But at the end of the day, right, what you have is you basically have a capacitance at the input, a capacitance at the output, and the idea here is to be able to have double the current, but the same capacitance. This is what I explained to you in the Cherry Hooper. So one of the ways to do it is to break down the dependence of the gain bandwidth product. And the figure of merit to define the gain bandwidth product is basically the FT of the process. So the FT can be doubled, multiplied by increasing the current or decreasing the capacitance. But that cannot be done on one device. We explained that why, right? So one of the ways to overcome it is to have the same periphery at the input. So notice all of these transistors all have the same input. The input doesn't change, but they drive the current in these two devices. So the input signal through the mirror double here. So this is the input signal is driving the current through this device and this device. So we're mirroring it. We're doubling it. The input signal through M1 is now changing the current here. Sorry, the other way, and changing the current there. So you're doubling it. Okay, so we can have a Darlington pair, we can have a mirror double, or we can have what's known as an FT doubler, where by adjusting these parameters, you can actually make the currents the same, the transconductance double, but the input capacitance remain the same. So if an exam I ask you to describe to you what's the difference between this and other different types of circuits, you will say, well, in this circuit, we're basically using a very simple concept of FT doubling by the equation of FT equal to GM over 2 pi CGS, decoupling the effect of gain and bandwidth, in which we can have more current, more transconductance at the available at the output, yet we still have the same single device input capacitance. So by definition, if we double the transconductance and the capacitance remain the same, we have actually doubled it. Any questions on that? Well, why do you have the resistor? So in this specific example, what we're really trying to do is we're trying to emulate the currents, right? So that they're equalized, so that the current through M1 is equal to the current of M2 for bias. Yeah, okay. For bias, yeah. Distributed amplifier. Okay, so we talked a little bit about this, and I think, I don't know if the concept was understood, but I'll just add another page after. Okay, so you have a circuit, keep on going to bipolar, same idea. And in this circuit here, you have, or it can be a FET, doesn't matter. Okay, the problem is you have resistance and you also have capacitance, right? This is the resistance of the trace or the parasitics or the lines, and this is the capacitance mostly dominated by the gate to source in the FET. Okay, so you have an RC, and that RC leads to a pole, and that pole basically induces the roll-off that we experience in high-speed circuits. Okay, so the problem is capacitance that is there and the reactance that it sees, especially the real part of that, right? That forms that roll-off, and there's really not much we can do. Or is it? What happens if I go back in red here? If I take the input node, but instead feeding it correctly, I actually distribute it. I generate a distributed model in which I actually introduce two inductances, L1, L1, same value. And if I have multiples of those devices, I can actually now form something that will resemble a transmission line. So you would have L1, 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 and I'll just leave it at that. And on the other side, I would have CGS1, CGS2, S, and CGS3, and so on. So now I've actually distributed, and of course there's loss there, but we're going to assume it just to be. So now what happens is I am no longer limited by the RC of the circuit. I'm limited by the properties of the transmission line. And that transmission line, remember, has an impedance, which is square root of L1 over CGS. And it has effectively also a cutoff frequency, which is 1 over 2 pi square root of LC, right? And it has a group delay. So we can do all of that directly, right? So how do we do it? Okay, well, if I have a transistor and I take the input and I connect it to a distributed pair. And I also do the same on the output because there's another pole at the output, right? And I'm just going to illustrate 3-stage device, but this can be n stages. And I continue with it. And I also continue with it, right? And I do the same on the other side. And I do the same on the other side. So now you have a wave that is traveling at the input. Let's just look at this. You have a wave that is traveling at the input. So this the input being the gate and the output being the drain, right? That's just a standard amplifier. In, out, in, out, in, out. So you have a wave that is traveling, right? And it's traveling along a artificial transmission line because it's formed out of the L's and the C's, with a constant impedance and an engineered group delay. And what happens is when it sees the amplifier, some of the signal goes this way and some of the signal continues the other way as well, right? But the signal that appears in the transistor gets amplified and it basically just shows up on the other side. So you have a signal that is being tapped, some of it goes into the amplifier stage and it appears over on the drain side. But this signal continues to travel, right? And as it continues to travel, it then sees the second tap. Some of the signal goes into the amplifier, some of the signal continues, and then it gets amplified and it will basically appear on the other side and it will be reflected in a forward wave as well. And this will go on. So if I purposely design the circuit so that the delay on the input side is equal to the delay on the output side, I can actually have the signals add constructively. You would agree? And effectively what I've done here now is I have a transmission line with another transmission line. So we have transmission line 1, transmission line 2, and they're basically separated by these tap amplification stages that have no frequency limitations because the frequency limitations of the amplifiers have been absorbed. Here's the key. I have absorbed the input and the output capacitance of the gain element as part of the lump element of an artificial transmission line. So let me just write it down. Oops. I have absorbed input, output, capacitance as part of the lumped elements of an artificial transmission line. Okay. So the amplifier is free to amplify. It doesn't have any frequency limitations. The limitations here is how high I can drive these transmission lines, which usually is much higher than I can drive the FT of an amplifier. And that's what it basically helps here as well. Okay, so the other component as well, and this is kind of a higher order thing, and we're not going to talk about it. You know how I said that if we purposely make the delay of the input the same as the delay of the output, when the signal comes out of the other end, it would actually act constructively? That is almost true, because in reality, obviously, what happens as well is that the phase will start to interfere and you're going to get gain peaking. So to reduce gain peaking, we purposely mismatch the delays of both. And that's an advanced topic that we will not cover in this course. Anyway, do we know what distributed amplification is? If I was to ask you. It's a FT bandwidth enhancement techniques by which the input and output capacitance of a amplification element gets absorbed into the lump elements of an artificial transmission line, and hence we're not limited by the RC pole of the active device, but rather by the properties of the transmission line. And that's what's shown here. You got multiple gain elements absorbed by these artificial transmission lines, with L's and the C's that you see at the input and C at the output. And that, what it does is that if I go back and look at this famous curve here, you see that you have your famous limitation, the gain bandwidth product is the first curve. And the point at which the gain is equal to 1, the bandwidth is equal to max, and that bandwidth point is equal to the FT, that's what FT stands for. And that's what you normally see on a lump amplifier. What does a lump amplifier mean? What is it understood by lump amplifier? Well, they can all be discrete, they can all be integer or discrete. In both cases, the definition is that it doesn't have any reactive element. Lumps, right? So you have cost. That's not really correct. It has basically the electrical length of the components that are making out that amplifier are small enough compared to the wavelength of operation. So there's no distributed effects, right? So if I put a voltage here, it will appear on the other side instantly because there is no delays. The moment that the electrical length becomes comparable to the actual physical length, then we have distributed effects, i.e. 4503, which you guys took last term, and then we have to distribute the model. And then we have to worry about phase and amplitude and how that rotates around that as well. That's what then we get into the second case here. So we have one limitation, which is the gain bandwidth product of lumped amplifiers. Amplifiers on which the electrical delay of each component is so small that it will really be that doesn't need to be analyzed as a distributed component. And then you have the second one, which is the Fmax, which is now a limitation on the rest, right? So we can bypass the FT, and there's many circuits that do it. The FT multiplier, which is many flavors and versions of it. So I would ask me, I think I asked you an assignment, right? What the tools are. Distributed amplifiers, Cherry-Hooper amplifiers, all of those. But ultimately, they are bounded by the Fmax, because after Fmax, there's no more debug, right? So there's a limit. There's a fundamental limit on the Fmax of it, but you actually get to enhance the bandwidth. So lump circuits are limited by Fmax and FT. FT multipliers are only limited by Fmax. Distributed circuits are only limited by Fmax. Very powerful graph. You need to understand what's going on there. I could just throw that graph and a question and say, explain me what's going on here, because I don't really understand. Yeah. It's supposed to be the same. Yeah, that's just that. So yes and no. There are two roll-offs going on when you have an Fmax, but the one that we care about should be the same slope as the FT. Which again, the interesting thing is that these all roll off at 20 dB per decade or 6 dB per octave, right? And we know what decade and octaves are. Similarly with this one, 20 dB per decade and 6 dB per octave, same slope. Okay. So, and when we talk about FTs and Fmax, it's really a small signal behavior. So we go back to the same as I asked you before. So what are we doing when we talk about FTs and Fmax? We're assuming that the signal that is affecting the transistor is so small that it doesn't quite affect the biasing point. So we can play around with GMs and CGSs and all this other stuff, right? But the moment that signal becomes large, then we got a problem with switching speed. So both FT and Fmax are small signal concepts, and they cannot be directly used to predict the actual switching speed of a device. Why it's important here is that when we're actually using high-speed electronics, what are we doing? We're switching ones and zeros. We're going all the way from the bottom to all the way from the top, and we need to get there fast enough. It's not a small signal behavior where the signal is so tiny compared to the biasing that we can kind of use small signal analysis, right? And that's the problem with it. FT and Fmax are good figures in there. It tells me how fast the process can be, but it doesn't directly relate to high-speed electronics or switching speed type of circuits in which we have inverters, right? So really the gate delay, which is basically CL delta V logic over I, is a better figure of there for circuits as well. So we're going to see what really happens there as well. So look at this curve here. So we have a large signal that is basically slewing. So the slew rate is the change of the output voltage as a function of time. That will tell me how fast you can fill out that capacitance or parasitic capacitance on that node. So this is all representative with respect to this circuit here. So you have an inverter and an E device with a current, and that's basically charging and discharging the capacitor CL. And the rate at which you do it is defined by the slew rate shown here, right? Which is defined by delta V over dt or ID over CL. But CL is basically, remember, the FT is GM over C. So CL can be decomposed into GM, ID, and omega T, right? So that's just comes out of this equation here, on the top right. And then something more important is really not define the FT or the F max, but actually define the power bandwidth of the circuit. So this is the better figure of merit to define how useful the circuits are on switching applications. So that is the maximum frequency at which full output swing can be obtained without distortion. What does that mean? Well, look at this curve here, right? Ideally, what I would like is a sinusoid signal at the input and an output that follows. It's an inverter, right? But the moment in which it's not fast enough to get to the end point, but it basically just makes it a portion of it, you actually have a distorted signal. And depending on how much distortion I would like to use as a figure of merit, and I can actually use that to determine what is the power bandwidth of that circuit. That makes sense? Okay. So slew limiting occurs if frequency is greater. Slew limiting occurs if the frequency is greater than the power bandwidth because of distortion, right? Here's an example of an amplifier input output. You have a slew rate, you have basically a tau, and then you can basically define the maximum steps that you can put in. A function of it, so you can do some manipulation of it. We'll have an example of this later. But a really interesting thing is, okay, so we talk about these FT factor that defines the speed. So we got two conflicting worlds in here. First one is the internal factors. So that is the intrinsic behavior of the process, right? We have we have a capacitance, we have a current, and then we can basically extrapolate the FT of the process as a function of the drive bias and also of the channel length on the device, right? That's a small internal factor that tells me how fast I can go. But I'll make use of that in a second to show you something really interesting. Slew rate on the other side basically says what the rate of voltage as a function of time, which is proportional to the amount of current available and also of the capacitance that it sees. And the actual rise time, the time that it takes from 10% to 90% is equal to whatever. Sorry, the time that it takes is the voltage level times the capacitance divided by the current. So we have the external factors, the power factors, and we have the small factors as well. Okay. And the basic CML design, as we'll define it, is a standard differential circuit that you have transistors M1 and M2 acting differentially. You have a resistive mode. The output is taken differentially DON, DOP, and then you have an I-tail curve that defines the current density for those transistors, and we'll talk about it in a second. So I-tail, W, and RL are basically your design variables, and they're fully commutating. So one is switched fully, and the other one is just basically the complement on it as well. And you basically, based on your 3509, you know that the load resistance is equal to the pitch swing divided by the I-tail, right? And the transfer function of this type of transistors, as we learn in 3509, 2507, and 4609, ID is the mobility of the device times Cox divided by 2 times W over L times the overdrive or VGS minus VT. Okay, but the problem is, here's the issue. To actually get more speed or to charge faster, you have to reduce the signal swing. Agree? Because if I reduce the signal swing, then the output doesn't need to go as far as it needs to, and I can probably get there faster, right? So if this transistor needs to go to 3 volts, and then all of a sudden I say, well, maybe I don't need to go to 3 volts. I can go to 2 volts. Then I can get to 2 volts faster. I can drive it faster, right? So we'll agree with the first statement, reduce the signal swing. We can also get rid of the loading capacitance. But that's not always so easy to do. Capacitance is a parasitic element, right? Remember how I said that the process for, well, a high-speed process can be defined by the kilogauges per millimeter that a process can do. And the smaller the form factor, the smaller the node that you're operating in, the smaller the capacitance because smaller size. But there are limits on that. So that is also another design parameter, right? So you can also increase the current. Having more current drive capability will allow you, if you think of a hose trying to fill out a pool, i.e. a transistor trying to fill out a capacitor, the larger the hose, larger the current, the faster that it will charge it, right? But also those are limitations because smaller gates and others have a limit on how much current they can actually handle. So reducing the signal swing is really not a convenient because then you will reduce the FT. Yes, if you make VGS low, what happens to the FT? Reduces proportionally. So FT depends, directly on VGS. So we can do that. Reducing the low capacitance, not really practical. Increasing the charge current, also not really practical, right? So that's if you want to speed up the charging process. If you want to both boost the speed and the bandwidth, which is the small factor, what do you need to do? You need to keep the minimum channel length smaller. But if you make the channel length smaller, that means that we're actually reducing the ability to have high currents. So one is actually contradicting the other. We need to reduce the threshold voltage, but reducing the threshold voltage also causes leakage, which again takes away from the transistor. So that's also not a parameter that we can do. Or we can increase the gate overdrive VGS. So look, so if you want faster charging, or if you want faster speed and bandwidth, they have contradictory requirements, right? One wants increased VGS, the other one wants it to be lower. Right? And I explain why. The equation for FT is directly proportional to VGS. But again, if I want to charge something faster, if I reduce the end point at which I have to get to, the end goal, that means I can get faster. So lower VGS for faster charging, higher VGS for higher speed. Yes.
Can you explain why, if you have minimum channel length L min, why does that conflict? Does that mean, like, just like you said, that doesn't mean it would be faster? So it would like increase the rate of
If you look at the transfer characteristics of a transistor, right? The actual ID is proportional to W over L, right? So you would think that making the L smaller would actually give you more current. But there's also limits on which the transistor, it's basically to do with the fact that the transistor can only handle so much before it breaks.
So you're saying we can have, lower the L to a certain extent, we can have so much current that will break the transistor.
Yeah, effectively. So those are limitations on the channel, right? So the channel can only support so much current.
Not be like a minimum length for the channel. They can say, okay, let's keep it at this minimum length. What a big transistor. But is not what L min is.
No, so L min is the minimum length that I can do in a given process. I can have any given length I want, but it's the minimum that we're really concerned with that gives the maximum speed, right?
So you can't reduce that.
We can all go beyond that. That's the physical optical limit of that process.
Okay. Is that what like like how we have speed and stuff like every year companies come up with products that
Yeah. Exactly. Yeah.
That speed is it's always limited by the size.
Yes. So when I talked to you, didn't take 469 with me, but when we talked about they call it a node, or a semiconductor node. That's basically a technology. That's basically a process that has to do. So let me give you some examples. 0.35 micron CMOS, 65 nanometers, 7 nanometer FinFET technology. What all the nanometer, 0.35 micron, what all those different parameters mean is the minimum gate length that we can have, which is effectively the length of the channel. But just keep in mind that when we're looking at transistors, right? So here's a transistor cross section.
It was like the size of the transistor, 0.3 nanometer.
No, the 3 nanometers. So if you look at it, right? So you have your drain and you have your source, and current is flowing
holes or electrons, however you want to define it, between the source and drain, right? So what we mean by the length is the length of the channel. There. And the width is the width of the channel, right? So the length of it is basically the amount of distance that you have to go to get from one side to the other as you travel the tubes. That's the length of the channel. So when you go into a 0.35 micron CMOS, this length is 0.35. If you go into 65 nanometers, it's 65 nanometers. If you go into 7 nanometers,
So it's like the channel on the side of the.
no, it's the length of the channel that matters.
Side.
No, length of channel, okay? Hey, that's important. We need to make sure. So, high-speed design considerations. To charge, you need lower voltage swing, reduce capacitance, and you need to increase the current. Because higher current allows me to get there faster, right? To boost up the gain and the bandwidth, we need to reduce the threshold voltage and increase the gain overdrive voltage by increasing VGS. So one wants the voltage to be lower, the other wants to be higher. That's a problem. Right? But is that something that we can actually take advantage of it? Question for you guys. Let's go back to this one. So if I reduce the 10 to 90% step, right? If I reduce a 10 to 90 step, where's my pen? My pen is here. So this is effectively your VG, right? So this is your VG. And you have a BG as well. If I can reduce the VG, right? I can reduce the time. And if I reduce the time, I can increase the frequency. But if I reduce the VG, on the bottom one, I reduce the speed and the bandwidth. Because FT is this gain bandwidth product. I'm shrinking it, right? Can I satisfy those two constraints all at once? Yes. Well, this one here wants the VG go up. Sorry, to go down. So this one wants the VG to go down. And this one, see, this one is not telling me anything about the VG. It's saying the VGS has to be up.
Even if you decrease the VG, your VGS will be smaller. VGS is VG minus VS.
Okay, but the question is, VG has to be smaller on the first one. Here is telling me that VG has to be higher or the same. So I don't want to reduce it. I want to maintain it the same. But what happens, but what I really care about is that the VGS will make the same. So is there a way that I can adjust the VG independently of the VS? Because VGS, right? VGS is VG minus VS. So if I make the VG what I need to for charging purposes, and then I purposely make this VS to be even lower.
Okay.
Right?
Okay.
So I push this even lower. So another design degree of freedom for high speed is reducing VS. So to increase VGS minus equal to get to VS, VG cannot be increased. Otherwise, you conflict with the single swing. However, we can reduce the size of VS. How do we do that? Well, if you've taken 4609 or if you're taking 4707, you would actually have probably been exposed to the transfer characteristics of the device. But you can see that if we were able to drive this transistor into something called current overdriving. So if you look at the voltage, VGS minus VS minus VTH is actually proportional to the L and W ratios. So I can change the L and W ratios to be able to push the VS. Right? So I can control VDS by using this equation. And if VDS increases, that means that VS is even lower. And then hence, I maintain the same gate voltage that I need for the charging part of it, but I have actually now lowered the VS by using that secondary equation. So you increase VDS, VDSAT, you lower the VS, hence
you maintain the same FT, but now with a lower drive, which again helps you with the charging part of it. So reducing WM or increasing the I tail. So you have reducing the W or increasing the current, basically allows the VDS stack to be increased. And that actually boosts up the FT because you now have a higher VGS factor there as well, assuming that VTH is the same. The problem is that this circuit here is not your standard inverter, right? What would you say about the pros and cons? So that is effectively what I now use as an inverter. But I spent decades trying to get to the ideal digital process, and I found that CMOS, complementary PNN, how about this, the perfect behavior because they have no static DC current, they're complementary, they're easy to design, and now I've replaced it with this differential pair with resistors and with an acyl current. So what have I given up here? Well, under overdriving conditions, the circuit now works not like a switching CMOS device, but a class AB amplifier. And as such, M1 and M2 are not fully turned on or off, like a class AB amplifier. And as a result of that, well, since no channel is forming, the charging and discharging process becomes faster. That's kind of the processing example of what is happening. Lowering VS is equivalent to reducing VTH, which makes M1 and M2 work under higher on-state current densities. And we'll talk about current density in a second. But at the expense of increased off-state power consumption, right? So basically, lowering the VG is the equivalent of lowering the VTH, which again have a higher current density, but it also means that the current itself is always conducting. So there's DC static conduction on that as well. Okay, now what is current density or current overdriving? If I was to, let me just insert another, what time is it? 12:40, okay. So if I was to look at a transistor and I have the current and also the periphery, which is the W, forget about the L is constant. But if I was to define this term current density as ID over W, and using standard units, I can basically say milliamps per micron, right? And I was to then plot performance indicators like FT and Fmax as a function of current density, you will now see that there actually are optimum points for speed. And that's what this one does. So you have a current density and you have speed. And you take any of those curves there, but you will notice that there is an optimum point on which you can have maximum speed as a function of current density. So if you are designing in CMOS, you're probably somewhere in here. Right? It's good for low frequency logic, low power logic, but it's not good for speed. If you're designing for high speed, you like to be somewhere in here, and that's your CML. So it all has to do with higher speed, higher overdrive, optimizing the current density of the transistor by simultaneously satisfying the conditions for higher overdrive and higher speed bandwidth. That's what I just said. So those concepts need to be stuck in your head when you're looking at this. Okay, what do they look like? So here are some examples. So you have your ITEL, and this here is a 2-to-1 mux, right? You can mux D1, D1B, or D2, D2B, depending on clock or clock bar. Standard. 2-to-1 mux, or you can do the opposite. You can do a 2-to-1 PMOX, right? You now have these inputs here, and then the outputs on the other side. Or you can do things like a latch, or you can do an XOR. But this right away, when you look at this logic, and this is available in any high-speed process, you can have CMOS or you can have CML standard cells. And these standard cells, which we didn't cover in 469, are actually defined as based on the principle of class AB amplification, current overdrive, and optimum current density.
And the current density, how do we fix the current density? The current density is fixed by
Controlling the current in the periphery. Because by definition, current density is ID over W. So how is that important? Let's say you're asked to go to Skyworks and you say, you know, it's your first day, but we're really tight. We need you today to design for me the fastest possible amplifier you can design. And then you're going to say, well, some crazy guy at Carlton once said that really speed can be almost estimated automatically just by thinking of current density. So if I have a 10 micron device, so W is equal to 10, I can really pretty much engineer the current that goes through it so that I can get the maximum speed. And what some fellow did in Toronto, and this was a student here, by the way. The student by the name of Fyodor Soldatsis then became associated with this researcher in New York under the direction of a professor that is related to the automobile region for the University of Toronto. And what they did is really just look at what happens. So it was almost like an observation of what processes do. But the interesting thing in here
Is that what they did is they looked at speed.
as a function of current density, IDS over W, remember? Milliamps per micron. And what they did is they said, okay, if I take a 90 nanometer, now you know what the 90 nanometer stands for, right? If I take a 90 or 130 or 180 or 100 or 350 or 450, the speeds are different. But the points at which the peak occurs is the same.
And then they did the same for F max. They said for F max, right here. Oops, F max right here.
For processes. The speeds are different, but the peaks are the same. And if I look
Even at noise characteristics, which are shown here,
the noise is minimal, different levels, but it happens at the same time. So something extremely powerful.
they said that if you know the current density, if you can control the current density by
Actually, ensuring that you have a current density of 23 milliamps per micron, you get the best possible FP. And if you do 0.2 milliamps per micron, you get the best possible F max. And if you get 0.15 milliamps per micron, you get the best possible noise. So if I ask you at Skyworks and you say, I want you to design an amplifier, but wait a minute, it has to be the lowest noise you can possibly get. So we'll have a starting point. I'm going to take, so let's go for noise.
So I'm going to take a device, and remember it's 0.15, right? So I'm going to take a device there, and I'm going to say, okay, I got 10 microns. I need to have a current density of about 0.15. What should the current be? Ten microns is the periphery. I need to have a current density of 0.15, which again is milliamps per micron. So I need to put 1.5 milliamps of current to a 10 micron device. That'll give me the lowest possible noise. 3 milliamps of current to a 10 micron device will give me the best possible FT. And 2 milliamps of current through a 10 micron device will give me the best possible F max. Right?
Bill, when it's a part of the circuit, the front of the two, which current to go with.
But that's what I'm doing now.
So what you want to achieve three different things. Like you want to lower it, you want to get loads on lowest possible.
Oh, no. Okay. So,
No, I said, if you were to be asked to do the lowest noise, you will use 1.5. If you're asked to do the lowest possible speed, you will use 3 milliamps.
Okay.
Okay, so I won't be here on Thursday, and we're going to start looking at, so this is an interesting paper. We're going to start looking at electrical signaling, and there is about 26 slides here that have a lot of material. I was hoping to get through that today, but I'm not. And I want to let these go through you guys as you go into your week, so you start to prepare for signaling, because now things are going to start to get a faster pace in terms of the understanding and the system level. So the principles are about us covered here. A little bit of timing, maybe one lecture on timing, and then we're ready to talk about system stuff. Clock data recovery, clock distribution, and right? So please go through that. I will try to do my best to cover the 26 slides in one lecture, and I will have that ready for you guys on Thursday. Yeah, so it's a lot of it is high level, but it's important that we understand those concepts. Every single slide in here has something that is so useful, so meaningful to high speed. So we have to at least own the concepts. The rest of it, can be done through manipulation, application, notes, equations, and all that. But the concepts are really, really important, right? Why are we afraid of capacitors in high-speed circuits? Thought we're all friends. Because why? Because we have DC blocks. You can have one circuit bias one way, another circuit bias the other way. It's almost like having a door, right? You can have one family here and one family on the other side, and they're not interacting with each other. But what high-speed tells you is, no, open the door, no doors. That's a problem. And why? Well, it's shown here as well. So, and then we really are going to start to understand I. So I have the worst possible case, what's called a non-return to zero. And the non-return to zero is important because when you have a 1 and a 0, but 0 is actually the absolute 0, then you kind of lose your reference. So we end up doing plus and minus as your 1 and 0, and you still keep the reference in the middle. So that's what the non-return to zero means. It's more energy efficient. On the scope of the course, we're not going to get into it, but that's what NRZ means. Non-return to zero, meaning the 0 is somewhere in between, so you have a plus and a minus, and finding the logical 1 and the logical 0. And then if you have constraints over the bandwidth, but you want to be able to put more data into it, then you do higher order modulation, which is the space amplitude modulation with 4 different levels. So we're going to basically understand what those 0, 0, 0, 1, 1, 0, and all that other stuff does, because we'll use it later, right? And here's an example of what I was talking about. If you look at the bandwidth of NRZ and the bandwidth of PAN4 for the same, right, you see that you actually need up the bandwidth in PAN4 to give you the same data rate that you can on NRZ. But that sounds great. Why don't we always use PAN4? Pros and cons. We'll talk about it on the next lecture. Okay. So again, we won't see each other for a while. We'll be until the 23rd, I think. But please review the material. And if you have any questions, Discord. Okay. You guys have a good reading week.
Thank you.